In this video, we're going to look at the kinematics of a particle moving in a straight line. Kinematics is an area of study that focuses on the movement of objects. It's not looking at the forces acting on them, it's just concerned with the movement. The vast majority of our work will involve what we call the constant acceleration equations. Often these are referred to the SUVAT equations. So let's go ahead and write SUVAT. So if you see in your book now SUVAT or the SUVAT equations, this refers to the constant acceleration equations. So we can only use these now when our models involve constant, or it might say uniform acceleration. Let's start off with S. S is the displacement. Displacement is a vector quantity, so it has magnitude and direction. The units we use generally is given in meters. Now, if I think about now the displacement, I might think about in terms of a scalar quantity, the distance. So the distance now, if I take this to be the x-axis, the distance from the origin might be 5 units. In the same way that the distance from the origin this way is going to be 5 units. But if we were working with the displacement, this would be -5 and this would be +5. So it has a magnitude, which is the size, and also a sense of direction. In the same way, if we were going up and down the y-axis, we would have exactly the same. So displacement, generally given in meters, is the distance, but it has a direction. So vector quantity versus a scalar one. U is the initial velocity. So it is the velocity that we start with. So initial velocity, generally given now in meters per second. Velocity again is now a vector quantity. Speed is the absolute value of velocity, it's a scalar quantity. So with velocity we have both a direction and this magnitude. So for example, I might be going in this direction at 2 meters per second and then in this direction at -2 meters per second. Yet if it was just a speed, we would say 2 meters per second. This is a final velocity. And when we say final velocity, we mean in terms of the model we're given. So final velocity, meters per second. So if we were travelling for, say, 25 seconds, the final velocity would be the velocity at the time 25 seconds. Quite clearly, if we went past 25 seconds, it might increase or decrease, but in terms of the time frame we're interested in. The next one is acceleration, or how velocity is changing with time. So acceleration. If this is a positive value, we will be accelerating. If it's a negative value, we'll be decelerating. So when you hit your foot on the accelerator in the car, you speed up. That's a positive quantity. When you hit the brakes, you now lose speed, or your speed decreases, and that would be a negative quantity. Yet again, acceleration is a vector quantity. It has both magnitude, which is the size, and direction. So let's now put this on, and this will be meters per second, or meters per second squared. Finally, we have time. So time, quite clearly, we know what time is, and that is given generally in seconds. So we've got displacement, which is the distance, but it's a vector quantity. Initial velocity, meters per second, it's speed with a direction. Final velocity, again, it's the last velocity we have in our model. Acceleration, if it's positive, it's increasing. If it's negative, it's decelerating. And then finally, we've got time. So if something's decelerating, it's losing speed or losing the velocity as time increases. Okay, so let's go ahead and look at these constant acceleration equations or SUVAT equations. Constant acceleration equations are the proper term, but in many books you'll hear SUVAT or some other form. You could have whatever, VUATs or whatever you wish, but generally it's SUVAT. Okay, let's look at one. First one, V is equal to U plus AT. Now, most of the questions we're going to get will give us 3 pieces of information and we need to find the 4th. So, for example, we might want to find the final velocity given the initial velocity, the acceleration and the time. We might want to find the initial velocity given the final velocity, the acceleration and the time. Or we might want to find time given now the initial velocity, final velocity and the acceleration. In this video, we're going to do some really basic examples. In later videos, we'll look at some more challenging problems, but for now, I just want to get some understanding of how to use and apply these. Often the SUVAT equations are daunting to begin with, but once you've written them down and used them a few times, they're fairly straightforward. Okay, let's look at another one. S is equal to now U plus V divided by 2 multiplied by t. So displacement, or the distance, is the initial velocity plus the final velocity divided by 2 multiplied by the time. Now you might recognise this from somewhere in the past, and let's just go ahead and draw something. What I'm going to draw is a speed time graph. So let's say we've got 2 points. So this now is going to be the time, and that's increasing. So let's say that's t seconds. And then what we've got here is the origin 0, and we'll have v meters per second. So you might have seen something like this in the past. So say this is going to be, let's say this is 5, let's say this is 15. So that's a speed, and let's say this is going to be after 4 seconds. Now if I drew a speed time graph, what I'm going to have is the following. We're going to have now a trapezium. So if I connected this up, let's just connect this up, we've got this scenario. So you might see this as a trapezium. Now the area of the trapezium is going to be now the base plus now the top. So the top and the bottom divided by 2 multiplied by the perpendicular height. So if I went ahead and drew that, we'd have something that looks like this. So we go across, we go up, then across, and like so. So this is something that you would have met before. So here's now my trapezium, and this is going to be the top. So top, bottom, and then we've got the perpendicular height just here. So we know that it's going to be t plus b over 2 multiplied by height, and that'll give me the area. Now if we look at this, this is exactly the same. All we're doing in this particular case is we're adding 5 to 15. This is the initial velocity, this is the final velocity. We're dividing by 2 and multiplying by the perpendicular height, and that would give us now the area under the speed time graph, which of course gives us the distance travelled. So in this case we'd have 5, that's the initial velocity, plus 15, which is the final velocity, divided by 2, multiplied now by the height. So we can see that that's going to give me, on here I've got 20 over 2, which is going to give me 10, and then multiplied by 4, so we could see that that would be 40 metres. So all we've done now is seen that one of these is something we actually already know. Another one we might see is v squared is equal to u squared plus 2as. So this might be a case if we wanted to find the acceleration given the final velocity, initial velocity, and displacement. Often with these equations, when you look at the information, you will look down and one of the equations will have the 3 pieces of information that you have and the one that you need. Another one, s is equal to ut plus 1/2 at squared. Finally, s is equal to vt minus 1/2 at squared. This one is less frequently used. It's mainly this one, and this one. So if you want to write them down, go ahead and do that, as we're going to work through some basic problems. So this video we will look at some easier examples, and then in the next one we will go on and look at some exam style questions. Okay, a particle has initial velocity 4 meters per second and accelerates uniformly at 2 meters per second squared for 10 seconds. Find the velocity of the particle after 10 seconds. Okay, let's pick some keywords. Particle. We've got particle just here and we've got particle just here. Also, we've got now uniformly. So this is accelerating uniformly. That means that we can apply the constant acceleration equations. If it's now got variable acceleration, we can't, and that will come later in our studies. Let's look at this word particle. When we're modelling up these scenarios, often they're unrealistic. But we use, for example, for a car, we'd use a particle. If we've got a car on a 3-mile road, the size of the car in relation to the model is tiny. Therefore, we can use what we call a particle. A particle has no dimensions, and as a result, we can centre its mass in one point. So another example, if you took now a marble and threw it up in the air, the size of the atmosphere or the air or the area that you're in is massive in comparison to the marble. So we would say that the marble is a particle, and we can model that up. So a particle must be small in relation to the bigger picture. So we've got uniform acceleration, so constant acceleration, we've got a particle, and now this essentially, we can see this moving now. If you want to see this now as the XY coordinate axis, this now is just a small particle moving backwards and forwards. In this case, we're going to be moving forwards in the distance or the direction of X increasing. So let's go ahead and write some of the information. So all I like to do is collect this up using SUVAT and decide which of these we need. So we want now on here the final velocity. That's what we're after. So that's what we're looking for, and I'm going to call that V. So that's what we're after. We're given the initial velocity, 4 meters per second. We're given the acceleration, constant acceleration, 2 meters per second, or 2 meters per second squared. We're given the time, and that's going to be 10 seconds. All of these are in the correct units, so I don't need to convert anything. It's not in kilometers an hour, it's not in minutes, it's all in the correct units. So what we want then is V. If we look across here now, the one that we want is V is equal to U plus AT. I want V, I've got U, A and T, and that's the one. So we're looking now for 3 pieces of information to find the fourth. So all I need to do is write that V is equal to U plus AT. So V will be equal to 4 plus now the acceleration, which is 2, multiplied by 10. So 2 times 10 is 20, plus 4, V will be equal to 24 meters per second. And that's a nice straightforward application of the constant acceleration equations. So we've taken our particle, it's moving in this direction, and we've worked out the speed or the velocity of it after 10 seconds. That's telling me now that it's still going to be in the distance, or in the direction I should say, of x increasing. Okay, let's have a go at another one. A car passes a point in the road with speed of 15 meters per second. 12 seconds later it passes a second point with a speed of 25 meters per second. Find the distance travelled given the acceleration is constant. So we've got constant acceleration, and we're simply now going to model this up again as a particle. So if you like, we can just go ahead and put that in now the constant acceleration equations. So collecting the information using SUVAT, I've got now an initial speed, so it passes a point. If you wanted to draw this up, what we've got now here is the following. We've got this scenario, so let's call this AB. Let's say that this is A, so it passes A and then passes B. We've got now this initial velocity here of 15 meters per second. We're going in this direction here. We end up now with the final velocity of 25 meters per second, and the time was equal to 12 seconds. So let's just plug this information in. 15 meters per second. We've got now on here the 25 meters per second. That's now the final velocity. We've got the time. The time is going to be 12, and we want now the distance. Okay, so we're looking for the distance. So essentially that's the displacement. So if we look at what we've got, then we've got the U, we've got the V, we've got the T, and we want now the S. So which one of these should we use? Well, all we've got to do is look at this one right here. Now you can manipulate this, but essentially I just want to use the information that I've got and just plug it in. So we can say S is equal to U plus V over 2 multiplied by T. So let's whack that info in. So we've got 15 plus 25 divided by 2 multiplied now by 12. So that's going to be 40 over 2. So we're going to have 40 over 2, which is going to give me 20. 20 multiplied by 12. So we're going to have 240. So S is going to be 240 meters. So I've used the information given. In some questions, we might have already worked something out. I'm going to suggest at this point now that you always try and use what I would call the clean data. The clean data, as I like to refer to it as, is the data that you're given in the question. So sometimes we work out, so for example now, if I worked out the acceleration from here, let's say I worked out V is equal to U plus AT. Okay, and then I said, well, I know 25 will be equal to 15 plus 12 lots of A. So from here, I could just subtract this, I could take that away. So 10 would be equal to 12A, and then I could say 10 over 12 is equal to A. Now, at this stage, I could use 10 over 12, or if you like, 5 over 6 in here, and I could say, well, I know this is 5 over 6 meters per second squared, and then I could use one of the other ones instead of using this to find that. So I could say, well, actually, I can use now to find this one, I could use V squared is equal to U squared plus 2AS. But I'm using a piece of information that I've just found. Now, it's perfectly fine if I've got that right, but if I've got that wrong, it's then going to mean all my subsequent solutions or answers to the question are going to be wrong. So, if you've got what I call clean data, that is the information given to you. Generally, it's better to work with that. Okay, let's look at another question. A particle moves with a constant acceleration of 3 meters per second squared in a straight line. At the point A, the particle has a speed of 4 meters per second in the positive x direction. The point B is 12 meters from A. Find the time taken for the particle to travel from A to B. So straight up with our SUVAT. So let's plug in the information and find that. So we've got now acceleration, and this is positive. So it's in the positive x direction. If it said the negative x direction, we would take the acceleration to be -3. So 3 meters per second squared. We've got now an initial velocity or initial speed. It's given a speed, but we're told it's in the positive x direction. So we can say this is positive 4 meters per second. What other information we've got? Well, we've got now the displacement or the distance, and that's going to be 12. So we've got 12 meters. I'm looking for the time. I want t. So I've got now a, I've got u, I've got s, I want t. Which one is that? It's going to be this one just here. So s is equal to ut plus 1/2 at squared. So we can say that 12 is equal now to 4, so let's write this in, 4t, and then we're going to have now plus, and we will have 1/2 multiplied by a, which is going to be 3, multiplied now by t squared. So what we can see here is that we've got a quadratic equation. So if I just rearrange this, we've got 3/2 t squared plus 4t, and then we've got -12, and that's equal to 0. So we need to go ahead and solve this. Now, looking at this, I could try and factor it. Alternatively, I can just put this through the quadratic equation. So a is going to be 3/2 or 1.5, b is going to be 4, and c is going to be -12. So let's now do this, and in the quadratic equation, so if you're not met the quadratic equation, t is going to be equal to -b plus or minus the square root of b squared minus 4ac all over 2a. So this will be now something that you've probably come across before, but we can go and sub this in. So what we're going to have then, we're going to have -4, then we're going to have plus, we'll start with the plus the square root of 4 squared, which is 16, minus now 4 times by a, which is 1.5, times by c, which is going to give me -12, all over 2a, which is going to give me 3. So quadratic equation for t, and that gives me now that t is 1.79, etc., etc. So t is equal to 1.79. Now I need the other value, so subbing this in, we can see now, let's go back, let's hit that, we want that. In fact, let's just go ahead and put that back in, as I seem to have lost it. There we go, now that's what I want, and sub that out, put that in. Now this time what we've got is -4.46. Now t cannot be a negative value, so what we can say is t cannot be equal to -4.46. Therefore we've got 1.79 seconds. So a slightly harder example, but all we're doing now is looking at finding the possible values of t. One is positive, one is negative, therefore we take the positive one, as t must be a positive value. As interesting as it would be, we can't go back in time. Okay, let's move on. Now, the examples we looked at so far have considered movement in the horizontal direction or the horizontal plane. We're now going to look at movement in the vertical plane. The vast majority of these scenarios is where we throw a ball up in the air or we throw a stone. There's only one slight difference to this. Now, when we're considering vertical motion, we look at a fixed acceleration, and that fixed acceleration is in the negative y direction, or it's going downwards, and that is rounded to two significant figures, 9.8 meters per second squared. This is what we call g, or gravity. So in all of your models, you will have now 9.8 meters per second squared, and that generally is given to be a negative value. Now, g does vary depending on where you are, but essentially for the purposes of this unit, we just take it to be that fixed value. When you're dealing with these models, often, well, I say often, more often than not, we take up to be the positive direction. It certainly doesn't matter as long as you're consistent in your working. So let's go ahead and look at some of these. A ball is thrown upwards with a speed of 6 meters per second from a point O. Find the greatest height the ball reaches above O. Now let's look at SUVAT. What we're going to do is look at SUVAT, and we will look at this very slightly differently. Now this is given not necessarily as the initial velocity, but the speed of release. Exactly the same thing, speed of release. Okay, so speed of release is the initial velocity. The final velocity, many of these models are a case of where a ball hits the floor. Students think if a ball hits the floor, the final velocity is going to be 0. We take it at the instant that the ball hits the floor. So what speed or what was the velocity as it hit the floor, not what is it going to be after it's hit the floor. Now, acceleration, if I'm taking up to be the positive direction, which I'll show on all of my models, this is going to be minus g, and that's minus g meters per second squared, or we can say now minus 9.8 meters per second squared. With these models, we ignore some of the forces acting on the particle. We don't consider, for example, wind or spin. These are very simplistic models, and later on in your study you might do something that is more, I'm looking for, I'd say, more complete in terms of the model. But for now, we look at something quite simplistic. We ignore spin, we ignore wind resistance. We take this to be a particle, whether it's a ball, whatever, and it's got a tiny, tiny size in relation to the model, and its mass is centered at one point. So a ball is thrown upwards with a speed of 6 meters per second from a point O. Point O generally means the floor or the origin. If you wanted to look at that on the XY coordinate axis, this is O. We need to find the greatest height now the ball reaches above O. So what I'm going to do is write this in terms of SUVAT. Now, it doesn't look like we've got a lot of information here. Straight away, I'm going to put the acceleration is going to be minus 9.8 meters per second squared. In your working, often putting g is helpful. Just you can leave it as g initially if you wish. Now, we've got the initial velocity, and this is going to be 6 meters per second. I'm defining up to be the positive direction. So I'm going to put here up is positive. Now, the greatest height means the final velocity is going to be 0 meters per second. And what we're looking for is h. Generally, I give this to be h. Now, what I've done, I've launched this ball up, and it's gone in a perfectly straight line upwards, and now it's stopped. The velocity at this point is 0. It's going to turn round and come straight back down. So if you wanted a model of what's going to happen, that is the very simplistic model. So here is O. I've now launched this ball from O. It's hit this point now where velocity is equal to 0 meters per second. You've seen that scenario. You've just think up in the air. You've looked at it and thought, that's going to come and hit me. That is the case. Velocity now is going to be 0, and this distance right here is simply going to be height. So let's go ahead and find that. We are looking now for h, the greatest height. So all we need to do is decide which one it is. I've got now to find s, I've got u, I've got v, and I've got a. That looks like this one just here. V squared is equal to u squared plus 2as. So v squared is equal to u squared plus 2as. So let's go ahead and sub in. 0 will be equal to u squared, which is 36, plus now 2 lots of a, 2 lots of minus 9.8 multiplied by s. S is h. So doing a bit of rearranging, we got h will be equal to now 36 divided by 19.8. So all I've done, 19.6, my apologies, 19.6. All I've done is rearrange this equation. If you want me to just step by step that, now I've taken now this over here. So if I multiply this by 2, what I've got is 36 minus 19.6h is equal to 0. I've said 36 is equal to 19.6h and then divided through. 36 over 19.6 is equal to the height. So let's go ahead and put that through a calculator. So you could, if you wanted, just put 2 lots of 9.8, entirely up to you. So 36 divided by 19.6, and this will give me now the maximum height. So 90 over 49, which is about 1.84. So we can say that the height is equal to 1.84 meters, and that now is given to 3 significant figures. So 3 significant figures. If you're working with subsequent problems, do leave that in as the exact value of 90 over 49. So let's put this in as 3SF. Now in this particular unit, lots of the answers are given to 2 significant figures. So the general convention is either 2 significant figures or 3 significant figures. I generally like to give 3 significant figures, or at least the level of accuracy of the question. Often you'll be told though to give to 2 significant figures. Just state what you're doing, and that's what we'd have. Okay, let's have a go at another one. A toy falls off a table and hits the floor after 1.2 seconds. In part 1, we need to find the speed of a toy. The speed of the toy hits the floor with. The speed of a toy hits the floor with. I think that's the speed of find the speed of. I think you know what it's saying. That's poorly worded. and then find the height of the table. Okay, let's draw this up. So what we've got is this scenario, and a little sketch isn't going to prove a problem. We can just do that. Now this has just fallen off the table, so it's come down here, and what we're looking for is this height. Now if this has fallen off, it didn't jump off, it wasn't pushed off, it didn't launch itself off. So right here we've got an initial velocity of 0 meters per second. Okay, we know we're going downwards, so all we've got to do is put this now in the constant acceleration equations using SUVAT. So what we've got then is the following. We're trying to find this distance h, okay? Now this time I could take downwards to be positive. So we could take downwards to be positive. So if that was the case, my acceleration is going to be 9.8 meters per second squared. Before, we saw that because I took up to be positive, it was minus 9.8 meters per second. But because I'm taking down to be positive, it's going to be positive. Initial velocity now of 0 meters per second. It has fallen off. Now, it falls off the table. So, initial velocity, and now what we need is the speed, and that is v. The temptation is to say that it's 0, because once it's hit the floor, it's 0. That is not the case. So again, we're going to use v squared is equal to u squared plus 2as. I want to now find h given on here. Apologies, I want to find on this one. Apologies, on the first one we need to do the speed, don't we? I've jumped ahead on that one. Let's put that in. So we got 1.2 seconds. Let's put that in. So we want now this one right here. So we've got now 0, we've got the acceleration, and we've got the time. So all we need for this one is v is equal to u plus at. So v is equal to u plus at. So we can say v will be equal to 0 plus now the acceleration, which is 9.8, multiplied by the 1.2. So 9.8 times by 1.2 in the calculator, 9.8 times by 1.2. And that's going to give me now, what's that, 11.76. So that now is our final velocity. So let's just put that in, and I'll say that's 11.8 at 3 significant figures. So velocity will be 11.8, and that will be meters per second. And that gives me now the velocity. So 1.2 times by 9.8. Okay, let's now find at the height of the table. So if we grab this information up, we got SUVAT. Now on here I've got h, I've got 0 meters per second, I've got now the acceleration, which is 9.8 meters per second squared, and I want to find now the value of h. Now what I could do here is sub in this part right here. I could put 11.8, but I might have got that wrong. So what I'm going to do is just put in now the 1.2, and that's time in seconds. So let's have a look what we want. We want this right here. I've got to find the h, which is s, I've got u, I've got a, I've got t. So if we look at this one, it's that one right there. So s is equal to ut plus 1/2 at squared. So subbing in, we can say h is equal to, and as soon as I stick 0 in here, it's going to be 0 plus 1/2 the acceleration, which is going to be 9.8 multiplied by 1.2 squared. So for a calculator, we can get the height. And this is what I said earlier about using clean data. I'm using information given to me in the question. So we'll do 0.5 times by 9.8 times by 1.2 squared. Times by 1.2 squared. So that now gives me, and let's say that's going to be 7.06. And again, that's the 3 significant figures. So we can say now that the height of the table, which is pretty high, it's a big old table, isn't it? 7.06. So h will be equal to 7.06 meters. So next time you're asked to sit on the table, it's a long way up. So again, you can see that often these models are not realistic, but if we use these equations, we know that we're going to get the correct answer given the information. Okay, let's have a look at this one. So we've got now a particle is projected vertically upwards with a speed of 10 meters per second from a point 4 meters above the ground. In part A, we're asked to find the maximum height reached above the ground of the particle, and 2, find the speed of the particle when it hits the floor. Now, with all of these, I suggest you draw a model. So a quick model is not going to hurt. So this is a model that I've got. Now, I've been told that it's projected upwards with a speed of 10 meters per second from a point 4 meters above the ground. So if we look now, what we've got, we could just say now that this is going to be 4 meters. So here's my 4 meters, okay? So 4 meters is just here. We're going to launch this upwards, and it'll do something like so. It'll come round, and then it'll come down to the floor. So this is the scenario that we've got. We need to find the maximum height reached above the ground. Now the ground is here. So if we look at this, let's model this up now. This is going up initially, and we'll write SUVAT just here. So we've got now an initial velocity. The initial velocity is going to be 10 meters per second. So we've got 10 meters per second. Now the final velocity is going to be equal to 0. I'm going to take up to be positive, so we can say that this will be minus 9.8 meters per second squared. So we want now, and I'm going to call this distance here, let's go for this distance, and we'll say that this is going to be h. So let's write h just here. So if we consider that that's going to be h, let's put h there, and let's put these in. We want h. So we're looking for this one, we got this one, we got this one. So we're going to use v squared is equal to u squared plus 2as. So we can say 0 will be equal to 10 squared plus 2 lots of now minus 9.8 multiplied by h. So h will be equal to 100, and again, all I'm doing is rearranging. That's 10 squared over 19.6. So let's go ahead and do that. So we've got now 100 divided by 19.6. So that gives me h. So that's h now. Let's just grab that back up. Let's have our answer. And that is going to be the 5.1. Now what we need to do is add it to the 4. So this total distance now, if we consider above the ground, is this. And we could call this now h2. So let's say this is h2. h2 is going to be equal to h plus 4. If you want to call it h1, that's perfectly fine. So that's what we got. We're just going to add 4 because we're considering now the height above the ground. We need to find the speed of a particle when it hits the floor. Again, I could use this information. I could do this as the distance. What I'm going to do though is consider again the clean information. So we got SUVAT. So now I want to think about this, and I'm going to take up to be the positive. Now if I take up to be the positive, let's consider the displacement. The displacement is going to be minus 4 because I'm going to end up 4 meters below where I started. So minus 4 meters. That's this distance right here. If I chuck it from here, it's going to come down here. Initial velocity we've got as for 10 meters per second, and that's positive. That's going upwards. I'm launching this upwards. Now we're interested in this value right here, which is going to be the velocity. We've got acceleration, which is minus 9.8 meters per second squared. So which one are we going to use? V squared is equal to u squared plus 2as. And this now is using the information from the question. So v squared is equal to u squared plus 2as. So we've got v squared is equal to u squared. So u squared is going to be 100 plus 2as. So a is minus 9.8, and then we've got s, which is going to be now minus 4. So if I now do the velocity, that's going to be the square root now of 100, and we're going to have now whatever this is plus 2 lots now of minus 9.8 multiplied by minus 4. So what we've got then is the following. Now if we look at it, the speed is the absolute value. Now if we consider this to be up, my velocity is going to be the negative. So when I take the square root, we should have the plus or minus, but it's just asking me for the absolute value, so the speed. So all I'm going to do is put this through a calculator. It's the square root of 100, and then we're going to have plus 2 times by, now I can put my minus 9.8 multiplied by my minus 4, and this will now give me the speed. Okay, and that's going to be 13.35. So we can say now that the absolute value is going to be 13, and we'll round this to 3 significant figures, 13.4 meters per second. So again, if you're given a level of accuracy, just aim to do it. So the speed of the particle when it hits the floor, because we're going to be 4 meters below. Okay, let's look at another one. A ball is thrown upwards with a speed of 8 meters per second from the point O. Find how long the ball is 2 meters or more above O. Okay, so let's draw a sketch. So here we've got O, and I like to do this on coordinate axis. You certainly don't have to, but what we're going to have then is the following. So we're going to launch it up, it's going to come round and back down. Let's say that this here is going to be 2 meters. So this is 2 meters. So if this is 2 meters, this is 2 meters. We're going to have some time here, t1, and some time here, t2, when it passes through. So on the way up, it'll be t1. On the way down, it'll be t2. So the total time, how long the ball is 2 meters above, is going to be t2 minus t1. So if we find this time and take it away from this time, we've got the time that it's going to be 2 or above. So let's go ahead and collect some information using SUVAT. So what we've got then is the following. So we want now S. This is the displacement or the distance. We want this to be 2. Okay, so we're going to put in 2. 8 meters per second it was launched with. We don't really not interested in that. We want now the acceleration, which is minus 9.8 meters per second squared. And what we're going to have then is t. Okay, I'm taking up to be positive, hence why I've got a negative acceleration. That's just g. So what can I say? Well, I want t. So let's go ahead now and see which one we got. T, A, U, and S. It's going to be this one here. So what we can say is the following. We can say S is equal to ut plus 1/2 at squared. So we're going to have now the following. 2 is equal to 8t. Now we're going to have plus 1/2 a, which is minus 9.8, and then we'll have t squared. If I rearrange this now into a quadratic, this now is minus 4.9t squared. So adding that to both sides, 4.9t squared minus 8t plus 2 is equal to 0. So all I'm going to do is solve this quadratic for 2 t's. The first one, the lesser one is going to be t1. The greater one will be t2. So let's go ahead. We've got now our a value. Our a value is 4.9. Our b value is going to be minus 8. And our c value is going to be positive 2. So straight through the quadratic equation, we can say that this is going to be minus b, which is going to be 8, plus the square root of 8 squared, minus now 4 times by a, which is 4.9, times by c, which is going to be 2, divided now by 2a, which is going to be 9.8. So minus b plus or minus square root of, again, if you square minus 8, it's the same as a squared, minus 4 times a times by c all over 2a, and that gives us this value right here. So that's going to be now our 1.32 and so on and so forth. So if I just write this here, what we're going to have then is 40, and I'll put the exact value. So let's just put this 40 plus 2, 2 root 155 over now, and what's our value? Over 49. And you'll see now that the other one is going to be 40 minus 2 root 55 now over 49. So if we look at that numeric value, and of course once you switch them over, let's just look at that, 1.32, and then if we switch these over to get the other one, this is a t1 and a t2. So that's the other one right there. So if I now do the following, if I just go ahead and say now 40, and then we're going to have plus 2 root 155 minus over 49 minus my answer, that will give us the time. So minus my answer, and that will give us this. That will give us 1.01, so we can say 1.02 seconds. So all I've done is looked at the following. This time here is 40 plus, so this one here is 40 plus 2, then we got root 155 over now on here 49. So that's the time it's here. The time it was here, and I'm giving these as exact values, 40 minus 2 root 155 over 49. So all we're doing is taking this time and subtracting that one, and that will be the time spent above or equal to 2 meters. So there we go. That's a slightly harder example. As stated, in the next video, what we'll do is work through some more problematic questions where we've got a lot more to deal with. But as you can see, this is simply a case of subbing them into the constant acceleration equations and solving for one unknown given 3 known values that we have in the question, or we can easily work out. So there's a brief introduction to the kinematics of a particle moving in a straight line. Yes, some of the models are very simplistic. Yes, it's highly unlikely that that would happen in reality, but it gives us a nice introduction to the topic. And later on in your studies, you will look at more realistic models and situations. So there we go, brief intro. In the next video, we'll go through some tough questions and look now at some different scenarios that we might come across.